Hey there, welcome back. My name's Chris, and today we're going to be building an I2C driver using C#. I picked up these sensors. They're temperature sensors. I don't really recall the part number for them. They were cheap, and somebody had requested a driver for it. Let's take a look and see what we've got. You can see this is a PCT2075. It's got an I2C address here that will be important. It also came with some pins, but this one has this quick connector that we can just use instead. For developing this driver, we're just going to use a Windows desktop, not going to use any embedded hardware to start with, just because it's faster. So I have this FT232. So we need one of these. Nicely. This avoids all the breadboard wires. We just plug this in and plug it in there. And that's all the wiring we need right there. Next up is the code. I've got open here the Meadow.Foundation solution. It is on the develop branch, so it has a bunch of external references. They're project references. If you pull the main branch, it's going to have NuGet, so you won't need all of these. We are working on a tool that will hopefully make it easier to set up the all of these folders and repositories. Again, if you're working on develop, which should work just fine for this, you won't have this external folder and all of these. So that makes it at least a bit easier. But I like having all of the project references just in case I need to debug into something else. So I'm going to go down to the peripherals. And generally speaking, what I like doing is finding something that is similar to what I'm working on rather than starting from absolute scratch. I rarely ever use the new project wizard. So we're going to come down temperature sensor. That seems pretty good. This one, it's got a drivers folder, so it means it's got multiple parts, but it's probably a good candidate. You can see it is a temperature sensor and an I2C peripheral, which is what we're after. It has this byte-com sensor base. To be honest, it's another thing I rarely use. I don't really like it. So we're going to use this as a template and do a little bit of messing around with it. So let's go over and open up this folder, root folder, and we'll do some copying and renaming and that type of thing. Again, this one has a drivers folder for multiple parts. We're not doing multiple parts, so if it had like a 2075 and a 2076, we would do that, but we're not, so I'm just going to get rid of it and the build outputs from the previous folder. Now we'll go up to the samples. This has 2. I only need 1. And then, very important, we need to go find the data sheet for this part. I've already found it here. It is over on the NXP site. Okay, so I've got the data sheet. I've got a skeleton for a driver. I'm going to get rid of this README file because it is for the previous one and our tools. When we go through and build it for publication, it'll generate it if it's not there. And we have our single sample. So we're all set to pull this into Visual Studio. So I'm going to add a folder for it and pull in the projects. All right, so we have everything pulled in. This sample, it's going to be broken because it's got a dependency on the previous library. You can see here. So I'm going to change that. And now I'm going to go through, starting with the driver. And again, first, we know that this is a different part. As I said, the byte-com sensor base I don't like, so I'm not going to use it. And then I'm just going to cut everything else out. I'm going to go into these other 2 files the enumerations. We know we're going to have addresses, but they're all different. And everything else that was in here is gone. So we'll find these addresses from the data sheet. And then similarly over in registers, in fact, this looks like it was using constants, which I don't like as well. So we're going to add an enumeration. All of those registers are going to come from the data sheet as well. All right, so I'll save that. Next, we've got these two interfaces that we want to implement because we know we're a temperature sensor and we're an I2C peripheral. So we'll just use the tools to fill those in. And now we've got a skeleton for the driver. Anytime I'm using an SPI or I2C peripheral building the driver, we've got a communications class, either I2C or SPI communications, that we can use for communicating with the bus. It takes care of some of the low-level stuff for us, makes it a little bit easier. So I'm going to create one of those, and we need the bus passed in via the constructor, so I will generate that communications in a constructor. So let's build that now. And here you can see we need to give it a peripheral address. Now you may recall on the part, let's take a look real quick. On the back side, it has, if I can ever get this thing to focus, it has an address, looks like 0x37. I think that's a 3. But what we would normally do is go look at the data sheet and see what it has for addresses. All right, so you can see that this thing may have a whole load of addresses. It's got 3 address bits, and if they're pulled down or pulled up, it tells you what the address here will be, and it actually depends on the package, but it looks like we've got 27 potential addresses for it, all with these different addresses. So I'm going to add these in, and the default I'm going to set to that 0x37, which is what is on this part itself. One thing we could do when we're looking at the addresses, we know it's hex. So hex here, 37 is the default, so the one that is open here. And if I take a look at that in binary, you can see it's 11011. And again, let's go back and look at this part again real quick. You can see on the bottom side, it's got this A0, A1, and A2, and then we have ground, float, and high. So those match this table. So A0, 1, and 2, and whether it is ground, so 0, float, or high. So we can set 27 different addresses, which means you could have up to 27 of these in your solution connected at one time. All of them are just floating, not connected to anything. And so that gets us this 110111 address, 110111, so 37. So I'm going to go through and add all of these to the enumeration. Because these are in binary here on the data sheet, I actually like to use the same thing in code. That way, if somebody's looking at the code and looking at the data sheet, they don't have to do any kind of translation in their head. So this is 1001,000, right? And what is that in? That's the fun thing here. So let's go here. 1001. These are 7-bit addresses, not 8-bit. And so this is 48. And so now I'll just copy the same logic down for the other 27 addresses. All right, so here are all of those addresses, including one at the very end that I call default, and I just alias it to this one. So now we'll use that back here in our constructor. All right, so now we have the construction of it. Next, we just need to figure out how to do a read for the temperature and really figure out what the capabilities of this are. You can see that it has 1, 2, 3, 4, 5 registers. That's it. So this is extremely easy. So now I'm going to define the registers over in the driver. Okay, so we have our registers defined. These match this table set here. So now really what we have to do is we need to add the functionality. One thing I did notice here is depending on the part number, we have a default for this, and for this, we might need to add that to the constructor, though we might also be able to just read it at startup because it is a read-write. We know that it's got a few different things. You can have a polarity selection, looks like operation mode either as a comparator or an interrupt. We can do normal or shutdown, so we can, put it effectively into sleep mode. For now, we can actually even skip all of those and just say, I want to only use this for temperature. As far as, as far as the driver goes, that's probably all we need to implement to make this thing useful. So let's take a look and see if it requires any operations to get temp or if we just can read it. Oftentimes you don't even have to do anything. You just power it up and read the register. Sometimes you have to send it a command to tell it to take a temperature or to put it into running mode. Here is a conversion that shows you how to do the temperature calculation based on the register. Obviously, the register doesn't have positive or negative. It just has a value in it. And in fact, you can see it's these upper bytes. So 0 through 4, these bits aren't used at all. So we have to take our value and right shift it 5 and then do all of our math on it. And in fact, this D10, so I guess bit 7 of the upper byte, again, it's not always super obvious, but bit 7 of the upper byte, so it's 2 bytes, is our positive or negative. So now to read the temperature, we know that this address, now take a look at this on the data sheet. It's a little bit interesting. It's a little bit unusual. The configuration is a byte, but temperature, over temperature, hysteresis are shorts, and then the idle is again a byte. So some of these registers are 1 byte, some are 2 bytes. Nicely, the communications library or communications class, this will help us out with this. We don't have to worry about all of this. So I can just go. Now I can do a read register. You can see read register here returns a byte, but I can also do read register as a U short. So this will bring back a 2 byte value. And so that should bring back the value in the temperature register. For now, I'm going to just return 0 so that it will compile. And really what we want to do is we want to see if this works, right? That's all we're after, is functionality to make sure that we're communicating with the peripheral. Now, if I come back over here to the samples, you'll see that this is for the Feather F7. So for one of these. I don't want to debug on that or deal with that. I actually want to use Windows. So my desktop, and just use that FT232 that we had talked about. This part here from USB right to my PC. So we're going to create another sample project that makes that easy. In fact, let's just modify this one here. So we'll take out all of the sample code. And instead of targeting the Meadow F7, let's add a reference to Windows and that FT232. So it's an I/O expander, the FT232. For Windows, we can't target Net Standard 2.1, but we can target .NET 7 or probably 6, 8. I think it would probably work 5 and up, but let's just go Net 7 because I know I have it installed on this machine. Another thing we have to do on this sample is we need to change this to an application. When I pulled in the Meadow Windows, it should have pulled in Core, but for some reason it does not seem to be wanting to. So we're going to override initialize here, and we want to use that FT232 I/O expander. All right, so as of this recording, the FT232 expander uses one of two underlying drivers. One is the MPSSE from FTDI. That one works for SPI bus. It has a bug and it does not work for I2C. So if we're going to do I2C, we want to not use MPSSE. Now we'll create our sensor instance. And we'll use just the default address. And then we have only implemented just this read. We want to see if temp register comes back with a value. And because we're starting up on Windows, we actually need to start the Meadow stack, which is as simple as that. And now we can debug this. All right, as is typical, I spent the last, 15 minutes fighting this, trying to figure out what was happening. It kept trying to deploy the app to a Meadow, even if one wasn't connected. And it was because I had this SDK still set for Meadow. So if we look at this one, it's got the project is a Meadow SDK. Once I change it to .NET SDK, then it will properly deploy. So let's get back to what I was working on. If I right click here, debug, start new instance, and it immediately comes into my breakpoint here. So what I wanted to look at is this sensor read. So let's step into that. And here we go. Temperature register, it says is E015, which my gut already tells me is incorrect. It's probably the wrong endianness. But let's take a look and see what that looks like. E015, right? So it looks to me like this byte and this byte are swapped. It's probably, that may not be the case. Let's go back and look at that data sheet, because remember, it is aligned left. Temperature is aligned left, so it'll have 5 zeros, E015. Okay, yeah, so they're swapped. See, we've got 5 zeros here, so we need to swap these 2 bytes. We've got a couple of options at doing that, but the nice thing is we can just tell it to swap this when we call this read. Let's change the byte order to big endian, and let's run this again. One thing to note, you'll see that I'm always doing a right click and say debug. Right now, the tools don't support, if I just hit start here, it won't work. It's going to try to deploy a bunch of things to the Meadow, which is not at all what we want. We are working to fix that, But just so you know, you have to right click on the project and say start new instance in order to get to this debugging. That's if you've got a solution that has a Meadow app and a desktop app in it, or I guess a Meadow F7 app and a desktop app. But here, so we're back to this. We'll step into this read. If we read this temp register, we look at it now, it says 1600. Well, let's take a look at that. That feels wrong to me also. I can't see that many of those bits being zeroed out. That feels wrong. Let's try to read it again. See what we get. And maybe it's right. 1620. 1640. I read it again and get 1660. There's something odd. Okay. So 1600, 1620, 1640, somewhere in there is what it's giving us. That doesn't seem out of the ordinary. According to the data sheet, the first 5 should be zeros. First 5 should be zeros. And this very high bit will be on if it's negative. It's not that cold in here, so it is off. So rough sanity check, that seems right. So now let's do the math. Basically, we're doing a 2's complement and multiplying by negative if that high one is on. For now, we can actually just look at, since we're not dealing with negatives at our initial test here, I can just take that, right shift at 5. So take all of these, right shift at 5, and then multiply it by this constant here. Looks like 1/8 of a degree. And that should give us a temperature. So let's try that. And let's see if that gives us something reasonable. And the beauty here with doing it on the desktop is I can just drag that up and run this, right? So it says it is 22.125 in here. And 22 degrees Celsius sounds reasonable to me. Let's come back over here. It says it is 72 in here. I don't think it's quite that warm, but that's at least a reasonable approximation. It probably needs some calibration. So we have that. So we could actually, again, I'm not dealing with negatives here. We'll have to still do the 2's complement because this is only a 9-bit value. But let's just continue with the positive. And so now let's go take a look at our sample app. We're just going to read it 10 times and report the result back out once a second. So we get our temperature here. And so you can see we are getting temperatures that are, it looks like they're within the reasonable range. All right, so I've updated the code here to handle the negatives. Basically, if it's if that high byte is, or that high bit is on, then we know it's a negative temperature, and we do a 9-bit 2's complement, and we return the result. So again, let's just verify that all of that works. It shouldn't make any difference because it's not going to run through that code because it's not that cold in here. But we'll make sure we didn't break anything. And we can see it's given values. Okay, so we know that we're at least reading this register. It's got some other capabilities. It's got hysteresis and I think some sampling intervals that we can adjust. But for a base driver, we've got at least the capability to read temperature. Now we do have a bunch of not implementeds in here that I'd like to, clean up. All right, so now what we really have left is some stuff dealing with sampling. So we've got our start, stop, and then our interval and whether or not it's sampling. First off, if you notice I've changed my shirt color, it's because it's a different day. When I went to edit all of this, I realized that, I don't know, I lost the footage from where we just were to the end. So I'm going to go back and revisit this and finish this up. You can see here that what's left are some properties, events, and methods that all deal with the sampling. So the whether or not it's sampling, how often it samples, the event for when it gets updated, and then these methods for start and stop updating. I could easily just go in and add a timer into this driver and implement all of that, but it's not necessary to do that. We've got some base classes in Meadow.Foundation that make this much, much easier. It'll take care of a lot of this stuff for us. So if we say, we know that this is a polling sensor, it doesn't tell us when data is available, so we have to poll for it. So it's a polling sensor base, and we know that it polls and returns temperature. And because we're in that same namespace, we've got to do this. So by making the polling sensor base, that then implements these properties and event, and that implements the start and stop updating for us. So you can see that this is hiding the read method from the sampling sensor base, which polling sensor base derives from. So really what we need to do is we need to override read sensor. You can see that just returns the same thing. So we just swap out read sensor for the read. And now we have an entire driver written. So you can see, including the usings and brackets and all of that, we have a fully functional driver in 40 lines of code. That's the entire driver. And in fact, our sample app that uses it is, well, it's got some comments and things like that, but, you know, it's also under 40. It's probably 30 lines of code. And that, again, includes usings, brackets, all of that. So we have, using the Meadow stack and the framework to build a driver, we have written an I2C Peripheral Driver in 40 lines of code, an app that consumes it in 30 lines of code using C#. There are very, very few, I would go on record as saying there are no other libraries that allow you to do this. If you want to be able to build things quick, build things fast and reliable, and the other nice thing here is you end up with a driver that has the exact same feel as 200 other drivers that behave the same way. So this is some of the power of using Meadow for doing development. Notice everything here that I used was open source. I used my desktop for hardware. I could move this to a Raspberry Pi. I could move it to a Jetson Nano. I can move it to, you know, some Meadow F7 hardware. I could move this to any of those platforms. No problem. So it was quick to do. It's reusable. It's extensible. And again, open source. So there are a bunch of compelling reasons that you would want to use this framework for doing driver and embedded development, especially if you are a .NET developer. That's all I've got for today. Thanks for watching.